this is a case where it's probably helpful to draw in the hydrogens. Maybe let's talk about this together. Now we have to decide whether these two hydrogens are equivalent or different to each other. And let me help you with that. At first it seems like they're different. And the reason it seems like they're different is that after all, this hydrogen is on a carbon that has a single bond to this tertiary carbon. And this hydrogen is on a carbon that's got a double bond to the tertiary carbon. So it seems like there's a difference in environments. Here, there's a double bond to the tertiary carbon, and here there's a single bond to the tertiary carbon. However, that's misleading because remember there's another resonance form where all these double bonds are shifted. There's another resonance form where all the double bonds are in different positions. And now the double bond to the tertiary carbon is for the top hydrogen, and the single bond to the tertiary carbon is down here. The best way to deal with this is, maybe you've seen this notation for benzene. Another way to write benzene is with a circle inside of a ring. And the circle inside of the ring just indicates that we really have two different resonance forms, two different places that the double bonds can be in. And this shows us more of the symmetry that's going on here. So when we're working with proton NMR, this is the least confusing way to write benzene. The best way to write benzene for proton NMR is like this. And then I think that makes it clear that these two hydrogens really are equivalent to each other. If you draw the circle, then we don't get confused about the positions of the double bonds, and we can see that they really are in equivalent positions. They're both on a carbon that's adjacent to the tertiary carbon. Does that make any sense so far? Mm-hmm. Okay. Well, then how about this? Should this be called B, or does it need a new letter C?
I would give that B.
Now let's think about that. This hydrogen is further away from the methyl group than this hydrogen.
Oh, already B. Sorry, that would be C.
Yeah. Remember, these two were the ones we called B,
Right.
because these were the A's over here. Well, this hydrogen is further from the methyl group than this one. Mm-hmm. How about this? Should this be C, or should it be a new letter D?
C.
That's right. Those are equivalent. And how about this?
D.
Okay. And how many peaks do we get total then?
4.
4. So the lesson here is that the best way to draw benzene for proton NMR is with a circle, so that we don't get fixated on exactly what the location of the double bonds is, because after all, there's 2 locations for the double bonds because of the 2 resonance forms. And that shows that there's more symmetry in benzene than you might think. All right, and now we're going to see that this is a very important exception. This is a case where we're going to have 2 hydrogens with the same connectivity, but they're still non-equivalent. So an important exception here is if 2 hydrogens have the same connectivity, but they have different cis-trans arrangements. If 2 hydrogens have the same connectivity, but one is cis to the other substituents and the other one is trans to the other substituents, those are still non-equivalent. I think this will be pretty intuitive once we see the example. So we could call these hydrogens here A. Then we could call these hydrogens B, or this one hydrogen B. Let's call this hydrogen C. I think it's pretty clear that this hydrogen is not equivalent to hydrogen B, because after all, hydrogen B is right next to the methyl group, and hydrogen C is further away from the methyl group. But now the question is, are these two hydrogens the same? Well, notice they have the same connectivity. They clearly have the same connectivity because they're connected to the same exact carbon. These two hydrogens have the same connectivity, but you can still see that they have different environments because this one is cis to the methyl group, and this one is trans to the methyl group. So this shows that it's possible to have the same connectivity and still have two different environments. If one of the hydrogens is cis to the other substituents and the other one is trans, this is a pretty important exception. You're pretty likely to see this on the exam. This comes up a lot. It's important to see how to deal with these double bonds, so it's good that we're looking at this. So this would be called then D, not C. Even though they have the same connectivity, they have different relationships to the methyl group over here. Of course, the reason why this matters is that there's no free rotation around a double bond. So this C over here is going to stay trans to the methyl, and this is going to stay cis to the methyl. So this one is always going to absorb in one place, and this one will absorb in a different place. So that would give us two different peaks. So this is our first exception. This is why I said before that the same connectivity only usually makes things equivalent. There are ways that you could have the same connectivity and still have different environments. Well, here's a good example. I think it's pretty clear that these do have different environments because one is cis to the methyl and one is trans. That was what I was trying to write down here. If you have the same connectivity but different cis-trans relations to the other substituents, you're still non-equivalent. So how many peaks did we get here?
4.
4, that's right. All right, that's a very important example to have in your notes. How many peaks here?
I'm gonna have to say 1.
That's right, 1 peak. There are no different cis-trans relationships here because there aren't any interesting substituents. So each of these hydrogens are in the same environment. So they would all get the letter A, and there's only 1 peak. Good. How many peaks here?
3.
3. These two, even though they're connected to the same carbon, they're not equivalent because the top hydrogen is trans to the fluorine and the bottom hydrogen is cis to the fluorine. So that's a good call. These will all get different letters and you get 3 different peaks. How many peaks here?
1.
1. Now, each of the hydrogens is cis to one of the fluorines and trans to the other fluorine. So they both have the same environments. So they both get the same letter. And there would be 1 peak. Good. When you're ready, how many peaks here?
2.
Now there are different cis-trans relationships. HA is cis to the chlorine, but HB is cis to the fluorine. How many peaks here?
1.
1 peak. This hydrogen is cis to a fluorine, and this hydrogen is also cis to a fluorine. So they really are in the same environment. And there's only 1 peak. Okay, I think you're getting the basic idea, but it's important for you to try to find more examples with double bonds to practice on, because that's something you're pretty sure to see on the test.